Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this is work with a lot of collaborators, my students at the ANU, collaborators from the University of Sao Paulo, and one of my better students, or best students, Chang, who went off to MIT for his PhD. Before I get into the talk, let me just give you a nice morning introduction. If you're ever in Canberra, or I invite you down to Canberra, you would know this is not Canberra actually, but this is just 2 hours from Canberra along the coast. You get an entire mile of beach to yourself. So if you haven't been to Australia, we do have funds for visitors, and I would encourage you to consider coming down. Okay, but back to reality. Okay, I'm going to assume this audience is familiar with graphical models. Okay, not all audiences are, but this one is. So I'm going to jump right into a continuous HMM, and I'm going to ask you how you might do inference in it. Now, this is not just standard HMM. It's not completely Gaussian. So you can't just do Kalman filtering. But let me define what I've got here. So I've got state variables b and x. B for broken, also for binary. So it's a discrete variable. I have x for position. So it's a continuous variable that changes over time. And on the position, I have some noisy observations, right? So the observation is a function of the position and whether the sensor is broken or not. Now, to define this HMM, I have to define sort of the prior distribution on the initial state, right? So I'll just choose a uniform, perhaps. I need to choose a sensor observation function. So I'll say if the sensor is not broken, maybe it's just sort of center of the true position. And the sensor is broken, maybe it's a bit asymmetrical. It tends to underestimate rather than overestimate. Okay? And also I need a transition, so I might just sort of choose some Gaussian transition function. So if I had a model like this, how would I do inference in it, and specifically closed form exact inference? Okay, so let me just show you what these inferences might look like. Here, this is the probability of observation 1 given when the sensor is broken, which is the, not broken, which is the blue line, or broken, which is the red line. Okay, so if it's not broken, you see if you sort of convolve the triangular with the uniform, you get sort of a nice Gaussian approximation. But if it is broken, you get sort of something very non-Gaussian here, due to the asymmetrical nature of the center model when it's broken. Okay, might look at a different function. What's the probability of the position at time 5 given the observation at time 01? So on the x-axis here is x5. On the y-axis going into the screen is 01, and the z-axis is the probability. Okay, so here's the actual function that I get. Okay, and if you're like me, you're thinking, what's that function? Okay, so I mean, if you look at it, it is not really Gaussian, right? So sort of it's bimodal, but I wouldn't use a mixture of Gaussians either because it sort of has this long peak. If you look at it sort of as a contour plot, you see it's sort of bent at the edges due to boundary effects with very sharp edges owing to the initial uniform distribution. Okay, so the question again is, how would you do inference if I gave you this HMM, this continuous HMM? Again, if it's Gaussian, you could do it, but it's not Gaussian. Does anyone do this in closed form? I'll ask. Okay, no one had said yes so far in all the talks I've given. And so I want to claim that no one previously did inference like this in closed form. Okay, I mean, if you're curious, that's what this talk is about today. Okay, now you might say, but we work with continuous inference all the time. Okay, and so I do want to cover some other ways, if you weren't exact, that you might do this inference. Okay, so people often discretize, right? So and then they not only discretize uniformly, they may adaptively discretize. Okay, so this is an adaptive discretization. In general, you're sort of bounded by the number of discretization points exponentiated to the dimensionality. So it's not great in high dimensions, but you can do it certainly in low dimensions. If you're adaptive, it does work, but it's typically an art form that's based on the problem you're solving. Okay, now one group of methods that are commonly used here, I know that are very good, are sort of projective message approximation methods, variational or EP. So you have some distribution. It might not be convenient to work with, so you choose the approximating class, typically a priori, often Gaussian. Okay, and while this does work effectively in practice, I don't want to criticize this, especially with this audience. I mean, it's always not clear that sort of your approximating class was the best choice, especially in a small data case where your posteriors are not typically Gaussian. And so I'm not saying these are bad methods, but what I'll tell you about today is perhaps one way to choose the best approximating class on the fly with these methods, and I'll come back to that later. Okay, and finally, sampling. I mean, sampling is sort of a staple of continuous inference going back to bugs. It is effective. It does work in practice, but there are a few cases where it does not work. So we know if the distributions are near deterministic or deterministic, we know it's not going to converge or not going to converge quickly. And if you have queries like this, where you might sort of say, well, I don't want to instantiate my observation or my evidence. I sort of want to leave it as a free variable. Well, if you're sampling, I don't know how to do sampling where you didn't instantiate your evidence, right? You'd sort of have to choose different instantiations and do the inference based on that. So this is one case where you might want to take the derivative of this expectation with respect to O, right? With O as a free variable, and I wouldn't know how to do this if I was sampling. Okay, so I don't think continuous inference is completely solved. Certainly there are lots of good methods out there, but I do want to tell you about a different method that I don't think anyone has used before. Okay. And so what is a different method? What's everyone been missing if they haven't been doing exact inference here? And I want to say it's the willingness to use symbolic representations and operations on piecewise functions. Most of the time, we want to choose a class like a Gaussian, which has a nice closed form, a mean and a covariance. We don't want to sort of work with something like Mathematica, where we just sort of do operations and the equations expand. But I want to claim, actually, you can do that, especially with certain classes, and it can be very effective and very expressive. Okay, and that's what this talk is about. Okay, so we need a symbolic form for general continuous distributions. Of course, it should be able to express things like Gaussians. It's a no-brainer. But I also claim that piecewise or deterministic distributions are quite common in practice. We need to support these as well. So if you work with stochastic programs, you often end up with conditionals. This gives you a piecewise nature to your functions. If you're like me and you focus largely on sequential decision theory, then you've got utilities, which give step functions often. So in some region, you get a reward. Outside the region, you don't get a reward. Decision making, you have a max. Okay, that always makes a piecewise, gives you a piecewise function. Preferences, I prefer A to B. Things like legacy and true skill, et cetera, introduce inequalities. So you want to be able to handle these, I claim. Again, for my work in controlled systems, switching control, not well, when your control system can be in different modes and your actions are discrete, this is not well solved in control, but it's an important problem. It requires these piecewise distributions. Okay, and finally, when I was interning here in 2006, I was looking at the Trusco model, and there's this delta function in there, which allows you to sort of sum variables, and that's a very useful thing. I mean, it goes back to bugs as well. But you often want deterministic equations in your models. So I want some form that can sort of handle all of these things. Okay, and what's that form going to be? Well, if you've been to high school, and I assume you have, then you'd represent case notation. I mean, in general, this is all you're going to need. Okay, so here I have a function on the domain x and y. Okay, in the blue, I have the constraints. Okay, just tell me which case partition that I fall into, and then say if x is 2 and y is 3, then I'll fall into this bottom partition. Okay, and then I'd evaluate this function with x and with x2 and y3. Okay, so it's a standard case statement. The blue is constraints, the red are values. I refer to the entire combination constraint value as a partition. Okay, now when is this a proper function? It's a proper function if the constraints are mutually exclusive and exhaustive of the domain. Okay, and in this case, the bottom constraint is negation of the top one, so that clearly holds. Okay, this will assign a unique value to every a unique z value to every value of x and y. Okay, so that's my general form. I will specialize it in a little bit, but for now, I'll say general. Okay, so let's just look at what we can represent with these functions. So here's a function. I'll tell you it has linear constraints and linear value. Okay, this function has linear constraints, and you'll note the tops are flat, so just constant value. It's even simpler. Okay, and this function, I'm going to let the audience guess. What sort of constraints would I need for these concentric circle? Polynomials, yeah, and even perhaps more constrained than just all polynomials. Just quadratics, yeah. So just x squared plus y squared is less than or greater than or equal to r. The value here might not be obvious, is also quadratic. Okay. So I mean, people often think of piecewise functions as these sort of Voronoi diagrams, but pieces can also be concentric circles. A piece could be sine of x is greater than cosine of x, right? So you'd have an infinite number of disjoint pieces, but only two actual cases. So in general, don't restrict how you think about the case statements. They're quite generic. Okay, so this is sort of the function that I'm going to work with. Okay, and so if I represented in my graphical model all factors with these case statements, okay, then I just need sort of a closed form piecewise calculus on these cases. I need to add and multiply the cases. I need to take the max and min of them. I need to integrate over them, especially in continuous graphical models. Later, when I do some sequential decision making, I might skip that today. Something I can talk about later. You would actually need to max out over a variable in a function. Okay, so in general, for inference that you need to do, you need to do these things. And the question is, okay, if my functions are in case form, how would I perform these operations in closed form since the result was a case statement? Okay, so let me go through that. Okay, so initially, so plus and times are going to work for any case statement, but because the rest of the talk is going to assume that the polynomial case, you can go ahead and imagine that the constraints were polynomial inequalities and the function values were polynomial inequalities. So if I want to do plus on these two functions, and I want a case statement as a result, first question for the audience is how many case partitions would be in the result, at least naively? So what? 4? Good. Right? So you sort of just take all, you could be in phi 1 psi 1, and in that case, your function value is f1 plus g1, right? Or phi 1 psi 2, and so on. So you just take the cross product and sum, okay? And if I wanted to multiply, right, then if this is multiplication here, then I just sort of change this to times, okay? So this works for a lot of the arithmetic operations that are closed for polynomials. But what about the max, right? So if I wanted the constraints to be polynomial inequalities and the values to be polynomials, then I couldn't, max wouldn't work out here. Max of f1 and g1 is not a polynomial. So the question is, can I do the max in case form? Okay. So can I do it? Okay, often the answer is no, but if you think about it, you can do an annoying trick. Right? I can say, well, if I'm in phi 1 psi 1 and f1 is greater than g1, right? This is still in the inequality polynomials, then I get f1, right? Or if f1 is less than or equal to g1, I get g1. So I'm just explaining the fact that max is a piecewise function, and I can represent those pieces easily as polynomial inequalities. Now those who typically said no to this function were a little bit annoyed, and they said, yeah, you can do this, but it'll never, it'll blow up. You'll never be able to do this in practice. Okay, and I fully agree. Okay, I mean, what I'm going to tell you today is just high school calculus at most. What kept people from doing it in practice was the fact they didn't have a data structure to keep things compact and to exploit the structure in these functions. Okay, I will get there. So far we've done plus and times and max, and these are closed form for polynomials. Okay, if I'm doing graphical model inference, I just now need to do the integral. Right? If I do the integral, I've given you everything that you need. Yeah. Now the integral is kind of fun. It's probably my most technical slide for the next 3 slides, and then I'll sort of pop up a few levels. Okay, so I want to do the definite integral from negative infinity to infinity, right, over some case function where the phi's and the function values f may involve the variable x. Okay, so how would I do this? Well, the first thing I can do is just rewrite it in more convenient form. So I'll use the Iverson brackets to say I want the 0, 1 indicator over phi sub I, and I'll rewrite the case in this simple summation form. I think it's pretty easy to verify that's equivalent. Okay, and if once I do this, I can now shifted the errors a little bit. I can swap the integral and the sum. Okay, and what does this do? It means now I only have to work on the integral for a single case partition, and then this sum here just becomes the circle plus, right, that I showed you before. So this is easy. I just need to show you how to do this inner integral. Okay, so I've simplified the problem a little bit. Okay, so it's best, I think, to do this in the case of an example. So here's a definite integral. My constraints are phi, so given here, and my function value is f1 is here. Now, if I didn't have the constraints, this would be trivial, right? It's just a polynomial integral. The problem that makes this annoying is the constraints. And so, how do I deal with the constraints? If you think about it, the constraints are doing nothing more than constraining the bounds of integration, right? So I know that x has to be greater than -1 and greater than y minus 1. Otherwise, the value of phi 1 times f1 is just 0 and doesn't contribute to the integral. So in fact, my lower bound is going to be the max of -1 and y minus 1. But I said I can do the max earlier. It's just a piecewise function. So here's my lower bounds, just a case statement. Okay. Likewise, for the bounds, x is less than or equal to z, and it's less than or equal to y plus 1. Okay. So it's less than or equal to, obviously, the min of both of these, and that's also a case function. Okay. So I can pull the blue and the red constraints into the integration bounds, and it just leaves me with this constraint here. Note that it's independent of the integrand, so I can just factor it out front. Okay. And I get this final form. So I've gotten rid of all the constraints, right? They were either put into the lower bound, the upper bound, or out in front. Now note that I didn't just write y greater than 0 here, because when I first did this, my student came back to me and he said, "Can probabilities be negative?" You know, this is always a scary question for your students. I said, "Well, no." But we looked at the operations. We realized, well, we didn't actually enforce that the upper bounds were greater than the lower bounds, and it's not always clear that it won't always hold if you don't constrain it to be that way. So for example, you don't know that z is greater than y minus 1. Okay, but we know upper bounds have to be greater than lower bounds, so we can just use pairwise constraints. We can add in z is greater than y minus 1, z is greater than -1, y plus 1 is greater than y minus 1, and greater than -1. So in these constraints here, you get not only the constraints independent of the integrand, but also these pairwise constraints on the upper bound greater than lower bound. You do this, everything works out well, and you get positive probabilities, which is a good thing. Okay. Now, I could do this very easily, except that I don't exactly know how to evaluate the bounds of the integration if they're case statements. So here's the problem, right? This was the integral. It's sort of this result evaluated the upper bound and the lower bound. Now, how do I do this, right? If the upper bound and lower bound were constants, it would be trivial. But they're not. They're case statements. So how can I evaluate this in closed form? Yes, okay, that's going to be effectively what happens. Very good. Okay, so we know that plus and times. So we know that polynomials are composed of plus and times, right? And this is closed form for case statements. So I can easily substitute in the upper bound into x cubed. It's upper bound times upper bound times upper bound. And once 1/2 x squared times y, it's 1/2 upper bound times y, which is a trivial single partition case statement. Okay, and because polynomials only involve plus and times, and plus and times are closed form, you'll note the entire partition integral evaluates to a case statement. Okay, and then if that's the partition integral, the last thing I need to do is sum for all the partitions, right? And that's also a case statement. So, voila. Okay, everything is closed form. Integration, multiplication, et cetera, everything I need for inference in this graphical model. So in general, your conditional queries are just integrals and multiplication, that's closed form. Okay? Or the exact expectation of any polynomial, right? The expectation of a polynomial is just some probability distribution as a case statement that I can infer times a polynomial, which is a trivial case statement. So mean, variance, skew, kurtosis, or your favorite polynomial, you can do all of these in closed form. And just like you do variable elimination on a standard graphical model, I call this symbolic variable elimination because you're working with these symbolic case statements. But you can generalize the idea here. And it's exact in closed form of this model. So come back to the initial example, right? If I'm willing to approximate all these as case statements, now here's where the assumption comes in, right? So triangular is that any uniform, that's a trivial case statement. Gaussian, is that a case statement? Well, obviously it's not from restriction to polynomials, but I claim that for any PDF you have, you can get an arbitrary approximation with a piecewise polynomial practice. And you still might be annoyed that I have to approximate a normal distribution by Gaussian, but I mean I claim you get low error, and the Gaussian wasn't even appropriate to begin with. So we might all agree that human heights are normally distributed, but I've never known a human less than 0 meters or greater than 3 meters. So I mean the normal itself is an approximation. Most distributions for real variables we see in practice are actually truncated. Okay. So in general, you can get an arbitrary approximation with a piecewise polynomial, so I'm not too worried about that. And once I do that, then all these functions here are just case statements, right, resulting from the multiplication and the integration. So now, right, I can do this inference in closed form, which I believe is the first time people have shown how to do this. Okay, now that's in theory, right? So this is all in theory so far. So this is nothing obvious. It's high school calculus with piecewise functions, right? What kept people from working with this in practice? Okay. Oh, sorry, I'll get there in a second. Let's just look at the complexity. The best case, you'll note that if my case statements if my case statements only had single partitions, then in the best case, I'd only have to do a number of operations equivalent to the number of variables, okay? Or the number of operations is the number of variables. So actually, in continuous variable graphical models, there are some nice lower bounds. For the upper bound, though, it's exponential in the number of operations. So on every case operation, if you have at least 2 partitions, right, it blows up. You multiply 2 cases with 2 partitions, you get 4. By another 2, you get 8, 16, so on. So it's exponential number of operations. The question is, how do you bound the number of operations and the number of variables? And I want to point out that it's not explicitly tree-width dependent. It's much worse. So the integral itself, you'll recall, involves plus and times and max just to the integral for the bounds and the substitutions, right? So the integral itself may involve hundreds of operations or exponential in that. So it seems really quite bad, right? It seems like we wouldn't ever be able to do this in practice. This exponential blows up way too quickly, okay? And almost somewhat as a surprise, I mean, I tried this out and it worked. Decision diagrams can really mitigate this worst case complexity and keep things compact in practice. Okay, so what I'm going to do from here out is I'm going to show you how to represent a case statement in a compact form that exploits its structure. But before I go into what I call the extended algebraic decision diagram to represent this, I first need to ask, are people here familiar with binary decision diagrams or algebraic decision diagrams? So can I see a show of hands if you know the BDD and the ADD well? Well enough to implement them in the next hour? Okay. So let me just cover some quick background then. Okay. So where I'm going is I'm going to represent the case statement as a decision diagram. Before I get there, I'll cover the background on the BDD and the ADD. Okay. So back to the discrete world, right, where things work out nice and cleanly. So imagine this is a function of A, B, and C. A, B, and C are binary variables. I know that I can represent a function as a table. The question is, can I do better than that? How about a tree, right? Trees are well known. So this tree exactly represents this table, and I want to point out that it's compact when you have things like context-specific independence. So you'll note that in the context of A being true, the value of the function does not depend on B, right? So that's called CSI. Okay, trees represent that compactly. Oop. But can we be more compact than a tree? What if we use a DAG in place of a tree? Right? Can anyone point out some inefficiency in this tree representation that we could get rid of?
Yes.
Right. C is redundant, right? We have exactly the same function C. Oh, my animation got lost. Okay. So how would I detect that? Well, the first thing from bottom up, I do a bottom up merging procedure. So before I had all of the leaves were separate. Now all the 0 leaves point to the same leaf. although one leaf points to the same leaf. And with simple hashing, right, if every node is represented by the decision variable and the ID of its true branch, sorry, I didn't say earlier that solid is true and dashed is false. So if every node is represented by the ID of the variable and the ID of the true branch and the ID of the false branch, I can just hash. And I note that these two functions are exactly the same function. Same variable test, same high and low branch, right? And so I can merge these. Okay? When I do that, and I have a strict ordering of variable tests from root to leaf, I get something called the ADD. Okay? And so it can be exponentially more compact than a tree. So it does exploit CSI, which trees it, but it also exploits shared substructure. So if you look at things like the XOR function, right, it's not a compact tree. I'll show you this in a few minutes. But it is a very compact decision diagram. Okay, now I want to point out that ADD is not only compactly represented functions, the operations on them exploit their structure. So there's something called the apply operation in the ADD. It allows you to apply any binary operation to two functions. So here's two functions that I want to multiply. Okay, how do I exploit their structure when I multiply them? Well, the naive thing to do that wouldn't exploit structure is I could convert them both to tables, do the operation on the tables, convert the table back to an ADD, right? But can I avoid that? Yes, I can actually build out the sort of the joint function that's required to represent the multiplication. And I can do this recursively. So I have a variable ordering, and I always want to branch from the first variable in either diagram. So that's going to be A. They're both shared. Okay? And I can look at, so what's the function multiplication when A is true? Well, here I get 0. And 0 times anything over here is going to be 0, so that's easy. Okay, so I just did the true branch. Now I do the false branch. Okay, so A false, I get to this subfunction here, right? And A is false here, I get to this subfunction. I need to recursively multiply these two functions. I can't do it exactly, so I branch from the first variable, which is B. Okay, and then I get to the two functions with C here. So B true gives me here, right? And I'm still here in this first function, and sorry, in the second function. So I need to recurse on C. Okay, you can sort of see that I can just do this and fill in the diagram. And the nice thing is, this operation exploits the structure. It's not going to branch on anything it doesn't have to branch on. And the result is provably minimal. Okay? Now you might want to say, what's the worst case blowup of such an operation? So imagine that I I had m nodes in this function and n nodes in this function. What's the largest number of nodes I could have in this function? So note that I can get one node in the result for every recursion. How many possible recursions do I get? Well, very naively, at most you get a recursion for every pair of nodes. Okay, so if this function has m nodes, this has n. The worst case blowup of this is to have m times n nodes, and that's worst case. It typically doesn't happen in practice. But the key thing is, if you have structure in your operands, you have structure in your result typically. Okay, so I want to point out the ADD not only exploits compactness in the function representation, but the operations. It also exploits efficiency of operations that exploit the compact structure. Okay. That was discrete. Now I want to go to the continuous case. I want to convert a case to the XADD. Okay, so I call this the extended algebraic decision diagram. XADD was cooler than CADD. Okay, so let me just show you what it looks like. So here's a case statement. Okay, and as an XADD, right, you use something like this. So the XADD, what are the properties of it? Every node is either an inequality. Okay, if it could be of polynomials. In this case, just linear functions. So it's either an inequality, that has a true or false branch, or a discrete variable. I don't have any discrete variables in this case. The leaves are just expressions. Okay, and there's a strict ordering of decisions from root to leaf. If I just had linear inequalities or polynomial inequalities, it would be trivial to sort of come up with some ordering. Any ordering you wanted on those decisions. Okay, so that's the XADD. Now you might, if you know the BDD and ADD, and you know that sort of given an ordering there, minimal canonical, you might ask, can I do this for the XADD? Yes, it's a lot less trivial because now, unlike the BDD and ADD, the decisions now interact. And I'll show you some issues that occur with this later. So it's actually much harder to reduce this to a minimal canonical form. You can do it, but it's NP hard. I mean, there's basically an embedded SAT procedure in it, or a SAT with linear equation solving. So it's something called LP SAT in it. And so my claim is you don't typically want to do this in practice. It's just too expensive. Correctness of operations on ADDs only requires the ordering. It doesn't require that you have minimal decision diagrams. And so in practice, actually, I do some heuristic minimization for the obvious cases. That's very efficient, but I don't always reduce these to a minimal form. And we have done it, and we should basically you're much slower if you try to do that. Okay, so that's what the XADD is. Just to think about the compactness, you might, from the BDD, you might recognize this as the XOR function. I just want to point out that this, whatever this function is, okay, it has a linear number of nodes as an XADD. But if you expanded this into a case statement, it would have an exponential number of case partitions, right? Because every path in this exponential number of paths is one case partition, right? So clearly, this can be exponentially more compact than the case statement. Okay, and just like the BDD and the ADD, the operations exploit the structure. So imagine I wanted to do a max of these two functions as XADDs, right? So I start with the earliest decision. So I'll say that's just arbitrarily going to be this one, y greater than 0. Okay, I branch true there. Okay, the next decision is x greater than 0. Branch true there. What's the max of x and the max of y? I don't know, right? So I've got to introduce a new inequality. Okay, and this points out that unlike the BDD and ADD, when you do operations on XADDs, you might actually introduce new decisions, right? This can happen, but that's fine. You can do it. Okay, and you can complete the result here. This is the max, the same max I showed earlier, but I want to point out that as an XADD, it maintains more structure than it would if you had a case statement. Okay. Okay. And again, the operations exploit the structure. The same bound you got for BDDs and ADDs that you sort of you blow up max as the product of the size of your F and G operands still holds here for the XADDs. That's quite convenient. Now, unlike BDDs and ADDs, you may get issues with orderings. So even if you do correct operations, you may get variables out of order because you introduced new decisions. So what if I knew that x is greater than y occurred before these two, but we note that when I did this max, the x greater than y got inserted at the end. It's out of order, right? It should come before these other two variables. Okay, so that's one issue. I can correct it. I'll show you in a second. I'm not going to show it here, but also when you substitute variables, you can easily get things out of order, and that's also a problem. And how would I correct that? So here's a simple trick. Imagine that I had z out of order with respect to subdiagrams 1 and 0. Okay. Now, I'm going to assume that these subdiagrams have been recursively ordered themselves. Okay. So now I need to get z in order. How can I do that trivially? Okay. So I can create the left half of the function as the subdiagram times the indicator. If z is true, it goes to 1. If z is false, it goes to 0. And I can construct the low branch of the function. And they're mutually exclusive, so I can sum them. And so arithmetically, this is equivalent to the left-hand side. Okay, but note now that this diagram's ordered. Z is trivially ordered, right? This is trivially ordered, and this is ordered. Apply preserves ordering, right? So the right-hand side is equivalent to the left-hand side. And if I do the apply operations, the plus and times to do this, then the result is ordered. So it's a very, very quick way to get a reordered diagram that also exploits caching that the apply operation does. So it's just a nice trick. So in general, the fact that you do get decisions out of order is not a problem in practice. There are other reordering methods. This is the one that I've found to be most efficient. Okay. Now, I did say earlier that the decisions do interact, and I do want to point out one unfortunate problem that happens here. So what if y is greater than 0 and x is greater than 0? Can x plus y be less than 0? No, right? You can never reach this leftmost leaf. So you'd want to print it out and promote the right-hand branch, the y, in place of this decision. Okay. Now, often in practice, I work with what I call linear XADDs. So linear constraints. The leaf values may be anything you want often, but the constraints have to be, or the decisions have to be linear. Why? Because I need to use the constraint feasibility checker of an LP solver to check the consistency of these constraints. You can do it for quadratic constraints and so on, but it becomes a lot less efficient. Okay, and so the question is how much. So there's other prunings that I can do as well here that I haven't shown. But the question is, how much savings do I get from pruning out nodes in these decision diagrams? So when I was working with MDPs, in one case we got a value function that had 1 million nodes, and we just couldn't compute further with that value function for any larger horizons. And so I implemented this pruning operation and went from 1 million nodes down to 1,000 nodes, right? So in general, the majority of the structure in these diagrams, if you didn't prune, would be unreachable. So pruning is absolutely crucial for efficiency in practice. Okay, so that's the XADD, right? So this is a diagram that allows you to compactly represent functions and do efficient operations on them. It supports all the operations I've shown previously. I won't go into those details, but it does, that exploit the structure of the decision diagram. And I just want to point out that it makes possible all the previous inference for the continuous variable graphical models. And you couldn't even do a single integral or continuous maximization without the XADD, right? Things just, I tried this initially and things just blew up. So that's really the secret that makes all of this work. Okay, so what else can you do with this? I'm going to wrap up, I think, soon here. I won't keep you guys too long. But just one exciting thing that I'm working on a lot with a new PhD student of mine is sort of very general Bayesian inference. So I don't think I need to tell you guys what this equation means. You have to prior your likelihood, your posterior for Bayesian inference. If the prior is an XADD and the likelihood is an XADD, the posterior is an XADD. And I claim you no longer have to choose your prior and your likelihood for computational convenience, right? You can choose these really ugly piecewise functions that are maybe appropriate for your task, right? Okay, and you can do the posterior enclosed form. Okay, now you might say, well, yes, you can do this for a little while, maybe for like 10 data points, okay, and then things are going to blow up. Okay, right? The XADD does blow up. It's not as much as the case statement, but it does blow up. So at some point, you're going to have to approximate. And this gets back to the point I made earlier, where if you want to do approximate method passing, how would you sort of approximate in a more structured way? I want to show you sort of as the last technical contribution an idea that we had in a UAI paper this year. And I'm going to leave you with an open question. If you can help me solve the question, then it'll help me a lot in future work. Okay, so sometimes no decision diagram is compact, but hopefully there's a bounded approximation that is. How would we do that? How would we find it? So in doing this work, I was motivated by prior work from around 2000 that was done in ADDs for approximating ADDs. So here's an ADD. It results from this function. I'm summing 2 to the I times xi, and then I add in some small epsilon noise times x4. Okay, and what has that noise done? If you just look at the leaves, it's basically just perturbed the leaves by small values, right? So 7.11 versus 7.06, 1.04 versus 1.01. Now, what if I wanted to approximate this diagram? How would I approximate it? It might be obvious given the leaves. I could just merge them. Whoop. Right? I can just merge them, right? I can merge these with their average. I can merge these with their average, and so on. Okay? And once you merge leaves, right, then you get rid of the need for x4, and so on. And so if you do an approximation like this, then you get a smaller diagram with bounded error, because I knew exactly the values of the leaves that I merged, so I knew how much error I introduced. And this is a very nice within structure approximation of an ADD. Okay, and so you could just keep track of the error, or here's a nice trick that was also used previously. You could use the leaves to maintain bounds. So here's an exact function, right? And so imagine that the leaves were labeled instead with a lower bound and an upper bound, right? So how would I approximate this function? I might merge the 9 and the 10 into a node with a lower bound of 9 and an upper bound of 10. And merge the 0 and the 1 into a node with a lower bound of 0 and an upper bound of 1, right? So I might get sort of, after I simplify, I'd get this function out. And if you're doing the operations, right, we know that to do arithmetic operations and so on with intervals, there's this thing called interval arithmetic, and it makes it quite convenient to do. It maintains the bounds. So this is a nice trick in practice for propagating bounds when you approximate. Okay, that's for ADDs. Now, how do I do this for XADDs? So take the step function, right? It's represented by this simple XADD. So you might think, well, this step function is nicely approximated by a nice linear function. How would I find the linear function that approximates it well? Okay, I'm going to do this in a greedy way because greedy is typically the most efficient. So I'm just going to look at pairs of nodes, say the two nodes for these two leaves, and I'm going to merge them. And now here's the question: when I merge, would I want to take the average of these two step functions? Well, the step function is the constant function, but no, actually a linear function is the best merge. So the thing is, you note, unlike the ADD, you don't want to average anymore, right? You want some better way to fit the function, and I'll come back to that in a second. But let's just say we found this as the best merge, and so we greedily add another node in. We find this linear function. Again, you can track the errors actually in the node. That's what the error here shows in the node. And eventually, you would just get a single linear function for this XADD. It has some error, but it's a smaller diagram and a small error. Okay, but you can't average leaves, right? That's not always the best approximation. So here's the general problem. You've got leaf values that live in two polytopes, and you want to say, is there some purple plane that best approximates, or that well approximates the two original leaves? So we're looking for an F that approximates F1 and F2 within the region of both polytopes. Okay, so obviously what I want is the F that minimizes the error, and so here I'll choose the absolute error between the purple plane and the blue and the green ones. Okay, and if you think about it, I mean, annoyingly, it's sort of a bilinear optimization problem. I have to look at the error at every point in these polytopes. Well, actually, I don't. If they're linear polytopes, then I know that the error always occurs the max error always occurs at the vertices. Okay, so in general, actually, I only need to have I only need to solve a problem of finding the best F such that it minimizes the error at all the vertices. So there's a constraint here for the absolute error at all the vertices. Problem is, there's still an exponential number of vertices here, right? So in general, this is not very efficient to solve in practice. But my favorite trick is constraint generation. Right? You can actually just sort of iteratively add in constraints, the constraints that most violate the current solution. Most people in the audience probably know this trick. And it's cool because if you had some setting of C here, how would you find the x's, the vertex that most violate the constraint? It's actually a linear program itself. But that linear program can generate x's at the vertex that maximally violate the constraint. And you can introduce those new constraints, and you iterate in a constraint generation approach. And typically, you only need to generate about 10 constraints in practice for a problem that typically has millions or billions of constraints. So my student and I worked on this very, very nice method for linear XADD approximation. Okay, and so here's the result. We were working with MDPs here, and here's some value function that we had. It's represented by this XADD. Just note that it's large. And after applying these leaf merging tricks to find the best approximation, you get this much smaller XADD, right? It was just made by merging and compressing within this XADD. And it's within a 5% error of the original function. So you'll note the linear artifacts, but the key thing is it's within 5% of the error. And so back to, say, variation or EP methods, the question is, can you come up with a structured approximation, right? So here's one way to shrink your representation while incurring a bounded error and preserving the shape of your function. Okay, but this is for linear XADDs, right? And we know that for graphical models, we needed the polynomial case, not the linear case. So this is a bit harder. We have F1 and F2. We need to find an F star that sort of minimizes the error. What error function do you want to use? What approximating class as well. But for the error function, well, I mean, the max error, say between two polynomials, is a polynomial programming problem. I don't want to solve that problem. That's a bit hard. But I can take the difference of the two functions and square it and then integrate it. Those are all closed form case operations. So I can actually compute the error, the volume of the squared error in closed form. And I can optimize that way. But there are many caveats. Unfortunately, the integral is not as efficient as the constraint generation approach previously. constraint generation approach for the linear case avoided looking at all the vertices of the polytope because it was doing constraint generation. When you integrate, you can't avoid looking at all the vertices of your polytopes, right? So this integral in practice tends to be quite expensive if you don't repeatedly and as many times as you need to do for approximation. So in practice, unfortunately, this is not going to be feasible. And this is actually a huge open question for me. How do I take this linear XADD technique of greedily merging and apply it to the polynomial case so that I can do nice bounded approximations of these functions in sort of Bayesian inference? Okay, so an open question. I'm working on it this year with a student. We have some ideas. I can talk to you offline about those. Okay, so I think I'm approaching 10 till. If I happen to come back later in the year, I will tell you all about sequential decision making, which is the application that motivated all this work. We later realized that actually the solutions that we gave here also applied to graphical models, and that's what I talked about today. So I'm not going to cover this actually, but we have some very nice solutions for continuous MDPs, and I just want to point out that we can actually, for the first time, solve optimally discrete action continuous MDPs, including the exact policy, and this allows you to solve problems like multivariate inventory control that were unsolved in practice for 50 years. There was a huge result in AAA last year. POMDPs and so on, all extensions, these are all sort of things that I've done previously in the sequential control area. And like I say, if I come back later in the year, I might get a chance to tell you about these things. But it's just basically noticing that in sequential decision theory, in addition to integration and multiplication, summation, you also need max. If you can do the max, then in fact, you can do all of these things as well. Okay. You can also do some interesting things in constrained opposition. This is only one slide, so I'll tell you quickly. If you had conditional constraints, right? So we know factor graphs are not just limited to probability distributions. We can also encode constraint models, say in factor graphs. So if you had a conditional constraint like this, actually I want to point, it's not, this slide's wrong. You could not encode this constraint in a mixed integer linear program or QP unless you use something called the big M trick. And then if you use the big M trick, you've got to tune M. Does anyone know what the big M trick is? No. Okay, sorry. In general, you sort of have to hack these constraints into MILPs and MIQPs, and people do it in practice. But I want to point out that you can do that in case statements. Furthermore, if I had a constraint system with sparse constraints, I could use dynamic programming to sort of work with that constraint system. And I didn't show you I didn't show you the max. I skipped sequential decision making, so I didn't show you this operation, the max over x. But it allows you to do things like parameterized optimization. So I can find, if I max out over x in this function, I get the function of y that represents the result. Typically, in an LP or QP solution, you wouldn't do such a thing. But with operational case statements, you can do what's called parameterized optimization. Okay. So I basically want to point out that beyond graphical models, you can also do very expressive things in sequential decision-making models and constrained optimization as well. Okay, so let me recap. So what did I do? What did I start off with? I defined a calculus for piecewise functions. I showed you how to do plus and times, max and min. I showed you the integral. I didn't show you the max and the min, but for certain cases that works out in closed form. Okay, and I defined the XADD to efficiently compute with the cases. Okay, so I can do all these operations in closed form fairly compactly. And what does it make possible? I can now do exact inference in continuous graphical models where my factors are in this case form. And I got some of the first exact solutions to many planning, control, and operations research problems. Okay, and there's also new paradigms for optimization. And so again, is the issue that statisticians and operations researchers and control theorists couldn't do high school calculus? No, that's not the issue. The issue is that they didn't have this data structure that could maintain these large piecewise functions in a compact form. I mean, statisticians and operations researchers and control theorists were never happy to use a gigabyte of memory to represent a function. But it is possible now. and that's what you can do. Okay. So in summary, I want to just point out that the symbolic piecewise calculus plus the XADD, this crucial data structure for allowing you to maintain things compactly, exploit that compactness in operations, allows you to do very expressive continuous inference, optimization, and control. And if you've been loath to think about doing symbolic operations in the past, I want you, at the end of this talk, to actually reconsider that, because these things do actually work out often in practice. Okay, and with that, thank you.
All right, we have time for some questions. Yeah?
Apologies if you covered this in detail before I came in.
No worries.
You talked about finding an ordering for your constraints or your, let's say, your polynomial systems. But it feels like things might heavily depend on that ordering, or some orderings might be
better than others. Yes. Generally, I mean, for the BDD, it's NP hard to find the best ordering. With my previous work with discrete models, I did work a lot with trying to find the best orderings. Typically, the amount of effort it took to find the orderings exceeded the time that it would take if you just sort of chose a decent ordering and worked with it. So
well, I'm thinking mainly for the XADD, you know.
Yes, so you have the same issues. You could search for better ordering, which would give you more compact XADD, but typically the time to search for it might offset the efficiency gained. The one thing with the XADD is you add in all these new decisions whenever you do the max operation. But it turns out, actually, it is right to add those last in the ordering, because they're very specific to certain parts of the state space. And you want the most specific inequalities actually to be near the leaves. So it turns out that when you're adding decisions, the way they're added in practice at the end tends to work best. But yes, I mean, if I have a very efficient way to find a good ordering, it would help. But I don't have a good efficient way to do that, and that's the problem.
I have a question about approximation. When you need to approximate, are you getting? It sounds like you are in fact getting exact upper and lower bounds on the approximation.
Yes.
With the interval arithmetic.
Yes.
Wow, that's very cool.
So for discrete models, for sure. For the linear case, we didn't actually do the interval trick. I want to point out that you can do it. I think you could easily. How far back is it? Almost there. I think you could easily change the constraints instead of the absolute error to be upper bounds or lower bounds, and do the same trick here. So if I want to extend this, instead of taking the best f that sort of slices through the planes, I want to take the upper bound, lower bound. I just change the constraints to do that, and then I'd maintain those intervals at the leaves. Yeah. So I think I could easily do that.
Also, could you give some sort of intuition about performance? I mean, you talked there about using a gigabyte to store a function.
Yes.
How did that arise?
Okay, so yeah, I mean, often these exact functions do blow up. I mean, not as bad as it would be with the case statement, but they do blow up. Performance is an issue. So graphical model, 20 continuous variables is about it depends on the structure, of course. But I typically can't do inference in more than 20 variable graphical models exactly. Because I don't yet know how to do this. I don't know how to do. So for exact inference, for the graphical models, I need polynomials, and I don't know how to approximate yet in a nice way for graphical models. So 20 variables is where I'm stuck out right now. However, if you're willing to do Gibbs sampling, right? One thing I want to point out is that you can do the conditional integrals. You can compute the conditional probabilities and the CDFs in closed form, and so you can easily do Gibbs sampling in these models. And so my one complaint about bugs is that you've got to do Metropolis Hastings, right? So you need to tune your proposal, and if you do Gibbs, you have none of that. So you can easily do Gibbs sampling in any of these models and avoid the need to do the exact closed form inference. And then you can also do many things that bugs cannot do. So bugs has many restrictions in practice. So I would say, I mean, I start off by saying how would you do this inference in closed form, but at at the end, I'm now thinking, well, sampling is not such a bad idea. I just don't want to have to tune my proposals and so on, like I would in bugs. And this method allows you to derive exact Gibbs samplers symbolically.
So Scott, when you were talking about DD pruning, were you sort of thinking about looking at which pruning strategies might be optimal for certain distributions of data? For example, if you have a training set, and you want to say, okay, I have a bound on the size of the DD, then what is the best pruning strategy for this set?
So strategy being greedy versus something else?
Yeah.
Okay, the only thing I know how to do efficiently is greedy, right? I mean, as soon as you look at merging multiple leaves, you get a sort of int-use k problem. Yes, you could get a smaller decision diagram if you did look at that, but in practice, I don't think it's worth the expense.
It also sort of depends on maybe what is the threshold at which you will allow sort of merging. So I mean, you can parameterize even your greedy strategy. And
yes, an excellent point, because the errors accumulate, right? And sometimes you might use up all your error to do a really horrible approximation and prevent things later. There's another, I worked on these things called affine ADDs for discrete models, and that problem definitely showed up there. It's a great point. I have looked at budgeting. So you know you're going to do in merges, so you allow epsilon over n error per merge. I can't say in practice that actually has helped things, but it's a great question. I don't have a great answer.
Okay, time's up. Scott will be here for pretty much the rest of the day, so if you're interested in talking to him, please let us know. And let's thank Scott again for